Hello everyone, and welcome to our first of two videos on acid-base chemistry. In this video we'll be discussing more of the quantitative aspects of acid-base chemistry, pKa's, and equilibria. So before we begin, I just want to state that we'll be using a Bronsted acid-base model for discussing acids. So if you're not familiar with that one, please brush up from first year. So Bronsted acid-base theory. Just as a quick recap, we will be defining acids as things that have protons. They will be interacting with bases, which will take a proton to form the conjugate base of the acid and the conjugate acid of the base. So this is our acid, this is our base, conjugate base, conjugate acid. Right, so an example of this in organic chemistry would be this reaction here. We have an alcohol interacting with hydroxide. That gives us the conjugate base of the alcohol and water, right, where each of those corresponds to the value drawn above. So things that we should point out that we have not seen before: this is an equilibrium arrow. Not to be confused with resonance, which is two heads on one line. This is not a resonance arrow. This is an equilibrium arrow, meaning that the amount of each of these is dependent on the energetics of each side of the reaction. So they can interchange until the energetic state is reached, where the lower energy state has, again, more compounds in it, and the higher energy state will have fewer compounds in the solution. Right? So again, we're talking about these things, drawing individual molecules, but everything that we're going to be discussing in terms of pKa's deals with things that are experimentally observed in flasks. So remember, there are lots and lots of molecules. We're just drawing one as a representative. So how do we determine equilibrium? Well, we can determine equilibrium using the equation for an equilibrium. This also allows us to determine which state is more populated, right? The products or the reactants. And which state, we can also refer to that as which one is more favored. So if we take our general reaction of HA plus B is in equilibrium with our conjugate base and our conjugate acid, we can define the equilibrium, right, as products over reactants Hopefully you guys remember that one. So for this, we can describe this as A minus conjugate base or conjugate acid, our acid and our base on the denominator. And since we're dealing with this in terms of acids and bases, we're going to relabel KEQ to Ka, which is the acid dissociation constant. All right. So this is the one we will be using. It's the same as that defined for a standard equilibrium. We're just very specific that we're looking at acids and bases now. All right, so let's take an example of this. HCl in water. Right, so if we look at the Ka of this one, going to put our products on top. So conjugate acid of water, conjugate base of HCl over water and HCl. So one of the things we can do here, and one of the things you'll see in a lot of equations, is that water is left out of this equation. That's because if we think about this in terms of the reaction that we're running, we're probably running this in a flask that is full of water, right? That's all water. And then we have a dilute solution of HCl added to it. So only a very small number of HCl molecules relative to the number of water molecules. So essentially the concentration of water doesn't change substantially throughout the course of this reaction. So we can say that that goes to 1 or is not changing throughout the course of the reaction. So you'll often see it neglected in these equations. Right? Another thing I want to point out, these are all experimentally observable and measurable things. So we can convert experimentally measurable things into a number that we can use for a quantitative prediction of acidity. So in this case, Ka is equal to 10 to the 8th, meaning that this is a very large number. This is small. And that means that we have a small amount of starting material and a large amount of product. All right, so for our next example, let's take a look at methane and its interaction with water, or potential interaction. So in this case, we would be forming the methyl anion and protonating water to give this reaction here. So if we look at the equilibrium of this, we would have CH3 minus and H3O plus on top, and then methane on the bottom. And what we find is that in this case we have a Ka of 10 to the negative 50th, which means that there's a very, very small number on top and a very large number of methane molecules, meaning that this reaction is heavily reactant favored. So in water, methane will not be protonated. And in fact, this will almost exclusively sit as methane in water, practically completely methane in water. So let's take a look at the two numbers that we have just generated in talking about our two systems. And we'll see that we are dealing with very large values, right? 10 to the 8th and 10 to the 50th. So these are kind of clunky numbers to have to be dealing with. So to simplify how we talk about these, we've converted this into pKa's, which is the negative log of the Ka. So in this case, a Ka of 10 to the 8th would mean that the pKa is -8, and a Ka 10 to the minus 50th would be a pKa 50 would be pKa of 50. All right, so notice here the very large pKa shows that methane is not being deprotonated. It wants to keep its proton and therefore is a very weak acid. Whereas a very low number or negative number suggests that HCl is a strong acid and was willing to give up that proton very readily. So all of this has been tabulated into data or into a table. Well, not tabulated into a table. Yeah. Sorry, guys. Redundant there. But you can see in table 3.1 all of the pKa's that have been assigned to different functional groups. And we'll be talking a lot more about functional groups in the coming weeks and their characteristics. But let's just take a look at this data. And so how to read this table is here. The proton in red is the proton that is being assigned this pKa. Your pKa is shown in the center. And then the conjugate base of that acid is shown in the next column, right? So you'll also notice a trend, and we'll discuss this more in the next video. Strongest acid, weakest base. Strongest acid, right, wants to give up that, is willing to give up that proton, which means that it's a very weak base because it doesn't necessarily want it back. So let's take a look at how to use these numbers, these pKa's, to assess the equilibrium of a reaction. So to start with, we'll take a look at the reaction that we looked at the beginning of phenol with hydroxide. And we'll spend more time talking about alcohols and phenols later on, but just as an example. All right, so here is the reaction. First thing to do is identify our acids. So on the starting material, our acid is phenol. On the product side, water is our acid. It's the conjugate acid of hydroxide. All right, so then we go to the table, and we see that phenols sit right here. They have a pKa of 9.9. Water is right there with a pKa of 15.7. So we know that a lower number is a stronger acid, which means that in this case, this phenol is our stronger acid. This is our weaker acid. And this is therefore our stronger base. Right? So we want to form the weaker acid. We want a weak acid and a weak base. Therefore, the product side is favored in this reaction. You will have more of the molecules sitting as a deprotonated phenol and water than you will in the phenol and hydroxide form. So this is a product favored reaction because we form a weaker acid. Okay, let's take one more example. And just for the sake of consistency, we'll just do that. All right, so in this case, we're saying that the terminal protons on carbon would be our acid. So we've identified our acid here, the conjugate acid of water. So if we look at our pKa's, we're now looking at pKa of around 50. And when we come up here, we see we have a pKa of negative 1.74. Right, so the difference here is massive. We have a 51.74 pKa unit difference. Which means that this really isn't an equilibrium. Almost all of the atoms or molecules will sit in the reactant form. Because remember, when we're dealing with pKa units, every unit is an order of magnitude. So the majority, not all of the molecules will sit as the alkane in water. And if you think about it, if you just mix an alkane in water, you're not expecting it to form a carbanion. All right, so this is how you use pKa data. You want to think about which is the weaker acid, and that's the one that's going to be formed. You can do that by using the pKa tables. In the next video, we'll talk about a more qualitative way of doing this if you don't have exact data for everything